Yeah. But yeah, it's just sad that you haven't been able to make it. But as I said, just we'll pick some other time where if you want, you and Simon wanted to come over for a week. We've got enough people here to make it interesting.
Yeah, we've wanted to come to New Zealand for ages, and then we couldn't because of COVID. And so then when someone invited me, I was like, yeah, I really want to come to New Zealand. And Simon was really jealous. So maybe we'll just come together on a holiday or something now.
Yeah. Well, maybe give it a bit of time. The North Island is trying to recover. So yeah, I'm now having thoughts about like we're going to have all these students who are coming from across the North Island who have all going to have lost lots of stuff, and it's like, how do we help them settle in the first few weeks? It's going to be anyway. Never mind.
Is the damage really bad?
Outside, yeah, in some places, yeah. So in Auckland, we've still got a few people who have not got power. So I'm getting emails from students and staff members who are saying, can I go in because I've got this deadline and they need power, and they don't have any at home. But then where I'm in East Auckland is actually pretty safe because we're basically covered from most of the wind apart from last night and the night before. But yeah, I know West Auckland is bad, and there are just some entire towns that are flooded, and the northern tip of the peninsula, the tip of the North Island is completely cut off because State Highway 35 is just basically shut. So it's not good. Sorry, that was all quite depressing. We should be talking about exciting gravitational wave stuff. So it's just nice we can all still be here, I suppose.
We have our big LIGO Virgo Cagra meeting in 3 weeks in Chicago, and I'm supposed to be flying to you to transfer to Chicago. So I'm hoping that your airport is recovered.
Yeah, no, the airport wasn't hit as bad as it last time, so it didn't get flooded. My mother-in-law is landing in on Friday, so I really hope she makes it back. But yeah, so you should be fine by then. So the flights are back up and running today. Some domestic cancellations, but yeah, so you should be, fingers crossed, fine. Yeah, but that's quite exciting, going to Chicago. It's a nice town.
Yeah, it's like 2 degrees and snowing at the moment, so I hope it warms up a bit over the next few weeks.
Yeah, I went during the middle of summer, so I used to have a friend who worked at Fermilab, and so I actually got to go to Fermilab as a PhD student and have a tour around and look at the detector. So but it's a nice city, and like the art museum there is just fantastic, because I think they've got one of the Great Wave prints as well, one of the very early originals. So it's really cool place to go and see.
Oh, that's cool. I have a few days to go and see some things, so maybe I'll go check it out.
Cool. Should we just carry on talking about our travel experiences for the next 2 hours? I think that's I think some summer schools should just be like, yeah, these are the places we go. As an astronomer, you get to go to these crazy places and see these cool things. That's just as useful as the gravitational waves. And Roy's cats are coming back. Sorry, Roy, what were the name? Somebody asked what were the names of your cats, Roy, in the chat. I don't know if you saw that. Oh, you're muted. You're muted, Roy. Roy, you're muted. We can't hear you. Yeah. Oh, we still can't hear you. The microphone's not working. While Roy tries and gets his sound back, I liked my joke about how I don't know if black holes have hair, but Roy's cats do, so that's good.
I like that joke too. I'm getting a new guinea pig after this.
Do we normally start these on the hour, or are we starting at 5 past normally, people? Should we start like a few minutes past, or?
I just waited until it seemed like we had the majority of people back, and it looks like we pretty much do now, so.
Okay. I'm just wondering how many people we actually have. Okay, we've got 25 participants. There was 40 registered, wasn't there? So we'll give people a few more minutes. Jade, did you want to try sharing a screen? Okay, cool. Yeah, we can all see that. We can hear you. We still can't hear Roy, but that's okay. So weird. Just give everyone a few more minutes. Yeah, the number of participants is going up. I think we can hear you now, Roy. No? Something happened because it's gone to you to say that you're highlighted because you said something. So what if you did? And now it's okay, never mind. we could try playing charades to guess your name of your cats. That would work. Okay. Sorry, Roy. Okay, we're close to 30 participants. So just people are joining. So I'm going to give Jade a shout out about what time? 12:25, just to tell her to we're coming to the first half of the talk for questions, and we'll have a quick break just so we're not sitting here for 2 hours. But otherwise, I will introduce Jade Powell, or Dr. Jade Powell, who's coming all the way live from Eastern Australia in Melbourne. So again, it's another speaker we would have loved to have in the country, but you know, it's one of these things. So I will let Jade introduce herself a bit more and take it away, Jade. Thank you.
Thank you. And thank you to the organisers for inviting me. I was very excited about coming to New Zealand. So my name is Jade. I'm currently at Swinburne University. I've been there for 5 years now. I did my PhD in Glasgow, and I worked like half on gravitational wave data analysis of supernovae, and then half on detector noise. And since I've moved to Australia, I've been working some on gravitational wave data analysis, and then also on supernova simulations, because at the time that I moved here, we didn't really have any very good waveforms to use for supernova gravitational wave studies. So I wanted to do something about that. I used to be chair of the LIGO Virgo Cagra supernova group, and now I'm the chair of the burst group. So all the bursts, including supernovae. So I'm very excited that I get to chair the group as we start the next observing run, and I hope that we'll find something that isn't a compact binary black hole this time, but we'll see. Okay, so this is a lovely poster by Carl Knox that shows all the gravitational wave detections that we've made so far. There's a couple of compact binaries in O1, then twice as many in O2, and then a huge number in O3. But so far, the only things that we've detected is binary black holes or binary neutron stars. But binary black holes and neutron stars have the highest gravitational wave amplitude, so we kind of expected to only see those at first. But as the detectors become more sensitive, we expect to detect a whole bunch of other things that emit gravitational waves. So in LIGO data analysis land, we kind of split up the sources into 4 different groups. So the first one is the compact binary neutron stars and black holes. Then there's continuous waves. They might be from like a spinning neutron star with a little mountain on it or something. And then there's gravitational wave backgrounds, which might be from gravitational waves left over from the Big Bang, or from just a background of lots and lots of overlapping binaries. But the area I work in is the gravitational wave bursts. So a gravitational wave burst is basically just any short duration signal whose gravitational wave signal is either completely unknown or we only have partial information about what the signal should look like. So I listed a bunch of potential burst signals here. So the one that I work on the most is supernovae, and they have a partially known waveform. So supernovae, we kind of know what the signal looks like if you take like a time frequency spectrogram, but in the time series, they have some stochastic element, which will always be stochastic. So you can do like a match filter search with a bunch of time domain templates like you would for a compact binary search. Then we have cosmic strings, and another source that we've started looking for in 03 is fast radio bursts. And we also look for gamma ray bursts, neutron star post mergers, magnetars. There's just been a 03 magnetar search paper submitted to the journal and put on archive in the last few weeks. We also look for binary black holes where the traditional match filter CBC searches don't do so well. So for these really massive black holes, they have really short duration signals, like sometimes just 1 or 2 spikes in the time series. And burst searches are really good at finding short and spiky things. And some like eccentric binary black holes, they just currently very poorly modeled. We don't really have any good waveform templates for those, so you can't really do match filter search for them. So they're covered by burst searches too. Then we also look for signals that are coincident with high energy neutrinos. And my favorite kind of burst source is the unexpected. So I hope that soon in one of our future observing runs that we'll just find some gravitational wave signal and we have no idea what the source is or where it came from. And we'll all have fun trying to figure out what's going on. And probably everyone will say it's aliens, but probably won't be aliens. And so I have this little diagram here, and this shows the duration of the burst source and the frequency. So for supernovae, they're pretty broadband in frequency and have all kinds of durations. And then some like the cosmic strings and like the IMVH signals have a really short duration. And then there's high frequency sources like the post-merger signals. And yeah, a whole bunch of things we look for in burst land. So the main search for gravitational wave bursts at the moment used by LIGO, Virgo and Kagra is called coherent wave burst. And coherent wave burst is designed to detect any kind of signal really without knowledge of knowing already what the morphology of the signal is like. And so the way that it does that is you need at least 2 detectors, and the signal has to occur in the at the same time in the different detectors, and also have the same signal shape. And then you would know it's a gravitational wave and not like just some random bit of noise. And so here's an example here. This is a spectrogram, so it shows the frequency of time, and this is GW 150914. So coherent wave burst hasn't made any burst only detections so far, but they've made some really good detections of compact binary signals. So the main one was GW 150914, the very first gravitational wave detection. So CWB actually detected it before any of the compact binary searches did. So I thought that was very impressive. And they also detected 170729, which was the heaviest binary black hole in 01 and 02, and 190521, an intermediate mass binary. So even though they haven't found anything that's not a compact binary yet, they're also making important contributions to binary detections whilst we wait for some other kind of source to appear in the gravitational wave data. So this is a kind of a diagram of how CWB works. So they use wavelets to make some kind of time frequency image of the detectors, and they calculate some maximum likelihood statistic to decide whether the gravitational wave is really there or not. This F plus and F cross here is the antenna patterns of the detector, which just tells you that how sensitive the detector is each sky location, because it's not quite all sky. And they combine the noise from the two different detectors together and compute their statistic, and then the output products are they can reconstruct the signal in the two different detectors. They produce a sky map of where the signal is on the sky, and they have this detection statistic that tells you how likely it is that this is a real detection and not noise. And they also have some waveform parameters. So because the signal model is wavelets, the kind of parameters you get out is like frequency where the amplitude of the signal peaks. So it'd be like this little red dot here, and you would get the duration and the amplitude of the signal. So I think that if we make a burst detection in low latency, that you will get told the signal to noise ratio, the frequency where the signal occurred, and also the duration. I think they all go out to get uploaded to GraceDB if we make a burst detection, but also sometimes we argue about that, so maybe that'll change in the future. And so we also have some other burst searches that you might have seen in some of the LVK publications. So one that was used in 01 and 02, and then they didn't use it in 03 because they ran out of people. And but it's coming back for 04 is a search called OLIB. And the O part of OLIB is this trigger generator called Omicron. And so all that Omicron does is it looks for excess power in individual detectors, and then it just gives out a massive list of times where there's excess power. Most of those excess power times are just going to be bits of enthusiastic noise. So then they cluster the triggers and search for which ones are coincident between two different detectors, or more than two. And then they just use a simple sine Gaussian as a signal model to analyze the data at the times where the excess power triggers are coincident between the different detectors. So a sine Gaussian, I have a little diagram here. This green is a sine wave, red is a Gaussian. Multiply them together and you get this sine Gaussian. So their signal model just looks like this. And then they use Bayesian statistics and produce a base factor to tell you whether the model is signal or noise. And we generally think that the signal is real if the base factor is bigger than 8. And so the OLIB search gives out a sky map. It'll give you the peak frequency, duration, and amplitude, the same as CWB, but it cannot reconstruct the signal. So because CWB uses multiple wavelets, they can reconstruct the signal and tell you what it looks like. But for OLIB, because they just use a single sine Gaussian, no matter what the signal is like, the reconstructed signal is always just going to look like one sine Gaussian. So yeah, that's the downfall of OLIB, is they can't tell you what the signal looks like. So also new for 04, we have this new burst pipeline called Emily, and it's currently being reviewed so it can be used in the generic search for short duration bursts. And it uses a combination of convolutional neural networks. It's mainly being run by this guy, Vasilios, who's at Cardiff University. And one thing that's different about Emily is that their search is only going up to frequencies of about 1,000 hertz, whereas the other burst searches go up to about 4,000. And so they have this little diagram that they've been showing everyone in their talks and posters. And so their neural network does a signal or no signal classification on the individual detector data. And then once they think there is a signal there, they use another neural network to do it on both detectors at the same time to say, like, is this signal coherent? Does it look the same in both detectors, or is it incoherent? In which case it's probably like two different looking bits of noise in the different detectors. And they get some final score thing out. So yeah, so Emily will be running for the first time in 04, and yeah, we'll see how they go. So once you've detected a gravitational wave, whether it's a burst or a CBC signal, then you have to say how significant is the detection, how likely is this that it could just be a bit of background. And so this little diagram explains how you do this, because you can just turn the gravity off and see what you measure. So it's kind of hard to measure the background in gravitational wave detectors. So you have two different detectors here, and this is their data going along in time. And then if you have a gravitational wave detection, they occur here in the same time. But if you want to measure the background, the way you can do that in a way that you know you're not measuring any real gravitational waves is you just shift one of your detectors in time a bit, so that the time between that you've shifted has to be, bigger than the speed of light between the two detectors. So it couldn't possibly be a gravitational wave. And then your real gravitational wave is over here in the one time, and then over there in the other time. So yeah, the real signals can't match up in time anymore. So if two things do match up in time, you know that they're just background noise and not real gravitational waves. And so that's how you measure the background in a burst search, to know if how likely is this to be a false alarm. So one of the biggest challenges for the burst searches is that we usually assume that gravitational wave data is non-stationary and non-Gaussian, but that's not really true. And there's many short duration noise artifacts that we call glitches. Here's some examples here from one of my papers. And they cause, so if you go back to this little diagram, when you have these accidental things lining up in time that you think might be a gravitational wave, but it's not, it's almost usually these things here that we call blip glitches. They kind of dominate the background in all of the short duration gravitational wave searches for both bursts and CBC. And we don't have no idea what causes them, so we can't get rid of them. So yeah, they're a big annoying pain for people searching for gravitational waves. But it's not even just the searches that are impacted by these glitches, because they also contaminate signals, and then that can mess up your parameter estimation. So this one here is called a whistle glitch, because that's what it sounds like if you listen to the noise. And then down here, this one is some scattered light. So they actually know the cause of this one, and they know the cause of the scattered light, but fixing it and getting rid of them all the time is really hard. So so you have like two kinds of glitches. These ones where we don't know what's causing it, we can't get rid of it. They only show up in data that's sensitive to gravitational waves. And then you have these ones where you know what causes it, but you just can't get rid of it yet. And so one thing that they have all over the detectors is a bunch of auxiliary monitors that are sensitive to all kinds of things. So some things that are easy to understand is like, earthquakes and lightning strikes and stuff like that. And so then if you have some excess power, some gravitational wavy looking event in your search, but then these auxiliary channel monitors also show one of these glitches, then it's not a real gravitational wave signal, and you just veto that little bit of data and throw it away. But because of these, we call them blip glitches, don't occur in any of these auxiliary channel monitors that are not also sensitive to gravitational wave signals, you can't veto them. And so they just dominate all of our search backgrounds as well as contaminating our signals. So another tool that comes from the burst group is called BaseWave. And BaseWave also uses wavelets to analyze signal. And they also use reverse jump MCMC to decide how many wavelets should be used and some other parts of their analysis. If you want to learn more about how BaseWave works, you can look at this paper by Neil Cornish and Tyson Littenberg. And so we use BaseWave for several different things. The first thing is they have this thing called baseline that estimates the power spectral density, which is like the noise curve of the detector. And having a really good noise curve really helps with your searches and your parameter estimation. So in low latency, baseline is too slow to make you a nice noise curve, but for offline things and for the parameter estimation, we usually use these nice baseline power spectral density curves. And then they also provide model independent signal reconstructions of the compact binary signal. So these are in a lot of the CBC detection papers. So here's an example here. This is GW 150914. And the red is a numerical relativity template. And the light gray is the reconstructed signal from using BaseWave. And the dark gray is from the CBC templates. And so it's a model independent way of saying that we think that this is definitely a CBC signal, and the model independent reconstruction looks like the template. So yeah, if they differed from each other, then we might think that maybe the signal wasn't a CBC template, oops, and that they just, yeah, and that there was still a bit of signal left in the data. So yeah, BaseWave's used a lot for that. And it can also be used to subtract glitches that contaminate signals. So here's some examples of where this was done before. So the most famous example is this signal here, which was the very first binary neutron star detection in gravitational waves. And in the one detector, it just had this giant, horrible glitch. And I thought this was kind of an easy case because you could just chop out this part of the signal and you still have all of this lovely bit of binary neutron star left. But for much shorter duration signals, you can just cut it out, because if you cut out the glitch like that, you'd be cutting out all of your signal and there'd be nothing left for you to analyze. So in this panel here, this is what the noise looked like after BaseWave had been used to subtract the glitch. So you only have this bit left down here, and you have this lovely compact binary signal there with none of this horrible glitch, and nothing just happened to be cut out and thrown away. And so there's also loads of examples of where this has been done in the gravitational wave transient catalogs. There's examples in GWC2 and GWTC3. So I just took this one example from GWTC2, and there's this horrible looking glitch here, these like 6 bright spots. And then after they run BaseWave to subtract the data, they got rid of these 3 spots here, and they're now gone. And you're just left with this nice signal here. So it's pretty slow at doing this. So a lot of people are still working on tools for faster glitch subtraction, and there's no way you could just run BaseWave on all the gravitational wave data and just get rid of all these glitches, because it would just take forever. They reverse jump MCMC is very slow. But yeah, but at the moment, when we still have a small number of detections, it's super effective at cleaning up the noise, as well as actually finding gravitational wave bursts in the first place. But in the future, when we have way more detections and everything is getting contaminated by noise, then we're going to need something faster. So it's still like a very active area of research that people are trying to work on other ways to subtract these glitches. So the main search for bursts is called our all sky short duration search. So I'll talk about that one first. And they typically search for any kind of gravitational wave signal that's has a duration of either a few milliseconds to maybe 1 or 2 seconds long. And they split the frequency range of their searches into 2 boxes. So they go from 32 hertz to 1024 hertz, and then 1024 hertz to 4096 hertz, which for me as a supernova person, I don't like this, because supernovae go from maybe 100 hertz to 2000 hertz. So you kind of cutting your supernova off in the middle. But for most other searches, they're not quite so broadband. So it probably works better for them. And yeah, and so CWB has been used for every all sky short duration burst search. So as base wave, OLIB was only used in 01 and 02 and wasn't used in 03, but I think it's coming back for 04. So I'll show you some of the previous results. So I'm only showing the coherent wave burst results. But these curves here are the background that comes from those glitches that I showed earlier. And so you need to be quite a long way above this, over here somewhere, to be a gravitational wave signal. This is their detection statistic, their coherent network signal to noise ratio, and this is the false alarm rate. So in the first observing run, the only event found was GW 150914, which is up here. And they didn't find any other burst sources yet. So then for O2, as you know, there was a lot more detections. And so this here is the number of events, and here is the false alarm rate. And so if you just have noise in your search, you expect to get this red line. And then these shadowy parts show you the sigma confidence of your detection as you get away from the red line. So you got like 1 sigma, 2 sigma, 3 sigma, and so on. And so the O2 all sky CWB search found all of these things here, which are all compact binaries that were published in GWTC as being a binary source. And if you remove everything that we're sure was a binary neutron star black hole, then you're just left with these events here, which are all pretty low in the 1 sigma box. So we don't consider any of those to be actual burst detections. And this is in the low frequency search. I didn't bother showing the high frequency search because they have nothing interesting in their box at all. It's currently, at least. And then in the O3 search, you can see here the same thing. The red line is where you expect if there's noise. And then this over here is all of your compact binary detections that was published in GWTC3. And if you remove all of those events that we're sure were compact binaries, then you only get these triangles down here, which are pretty consistent with predicted noise. So yeah, no all sky burst short duration detections during 03 or 01 or 02, but I'm keeping my fingers crossed for 04. So next we have a long duration burst search, and the long duration bursts go from 2 seconds to 500 seconds, and they search the frequency range of about 20 to 2000 hertz. So when we do searches, we usually do the search and then we take a bunch of templates for potential signals and add them to the noise, and then search for those signals to see how sensitive we would have been to them if they had occurred. And so in this list of potential sources, we've got non-axis symmetric deformations, magnetars, low mass eccentric binary black holes. So the high mass ones you would detect in the short duration search because they are they are short duration. And then if the mass is lower, the signal gets longer, so they also look for some in the all sky long duration search. We also have a specific CWB search for eccentric binary black holes, where if I go back to CWB, yeah, so when they make these time frequency plots, they usually have no constraints on what the signal should look like. They just use the wavelets. But for the EBBH specific CWB search, they tell it that they have this condition that the signal has to rise in frequency with time. So we also have a CWB EBBH specific search, but that paper hasn't been released yet for O3. So I can't show you the results, but there's like a finished paper draft that's being circulated within the collaboration. So hopefully you'll get to see that one soon. Then there's also accretion disk instabilities and fallback accretion onto black holes. And they have two search pipelines. There's a long duration version of CWB and another pipeline called STAMPAS, which I didn't write how it works because I don't know how it works, which I probably should go and learn. And so here's a diagram that I stole from the O3 all sky long duration burst search, and it just gives you some examples of what the duration and the frequency of some of these signals look like. So this is the innermost stable circular orbit of some binaries that have like high frequency and not that long in duration compared to some of their other sources. And then the magnetars are over here, high frequency and in the middle of their duration band. And then this ECBC is eccentric binary black holes. And I do not know why they called it ECBC instead of EBBH, but that's what that is. And they have all these different kinds, which gradually get longer in time, but still around the same frequency. And they have some GRBs, and then this is the accretion disk instability, which gets really long. And then this is a white noise burst or a sine Gaussian. So it's just some ad hoc signals that they've used to represent burst sources that could potentially be there, but we don't really know what they are. So the same for the all sky long duration burst searches, they have made no detections so far. And the only thing that they've done is they've been able to place upper limits on some of the potential sources. So I don't have a plot of the results of the search because they didn't have a nice plot in the paper. They just had a boring table. So I thought it was easier just to say no detections. And then in this plot, this is the distance and this is the rate upper limit. And then this is all of those different EBBH waveforms that they had here. So the different letters are different durations, and they put some upper limits on those. So yeah, maybe they'll find something in 04, but who knows. So another burst source, which we only recently started looking for, is fast radio bursts. So LIGO and Virgo have an MOU with CHIME, which is a radio telescope in Canada, and they're currently making a huge number of detections of FRBs. And so far, we've done a search for gravitational waves coincident with those FRBs for O3A, and we're still working on the reviewers' comments, so it's not quite published yet, but the paper's on archive. And the O3B search hasn't been finished. They're having some technical issues with their code, so you still have to wait a bit longer to see if we detected any coincident gravitational waves with fast radial bursts in O3B. And so no one really knows what fast radial bursts are, but if you look on archive or something, you can find 1,000,001 crazy explanations for what they could be. But some of them are types of binary neutron stars. And so in the search for fast radial bursts, we use two different searches. One is a version of PyCBC, the CBC search that assumes that the source is some kind of binary neutron star. And then there's also a burst search called X-pipeline. And so X-pipeline is kind of similar to the other burst pipelines in how it works, but it kind of only runs on these kind of targeted searches instead of, all sky, any kind of source search. And so the burst part of the search, they look for 600 seconds before the FRB and 120 seconds after the FRB. And they look for just regular fast radio bursts, and they also look at the repeating fast radio bursts, whereas I think for the compact binary search, they don't look at the repeaters. So this is the results from O3A. So if you had detected a gravitational wave coincident with a fast radio burst, then these little blue dots would be expected to be outside of these gray dots. And this is the fraction of FRBs, and this is the p-value. So we didn't make any detections because all of these little blue dots are inside these black dots, where they would be outside if there was a detection. And one of the interesting things about the fast radio burst search is that we put upper limits on the distance and number of FRBs. So at the moment, the binary neutron stars that we've detected have been the fast radio bursts that have happened during O3 was further away than the maximum distance out to which we could detect binary neutron stars. But we're detecting way more binary neutron stars and getting more sensitive to those, and we're detecting more fast radio bursts all the time. So one of the things that the rates is expected to be maybe 1 or 2 in O4 will be a fast radio burst that's actually within the binary neutron star detection range. And so we might be able to rule out a neutron star as the source of a fast radio burst, for the first time. So that might happen in O4. So I have a lot of slides on supernovae, so I don't know if you want to stop here for the break, just because it might be a more natural time to stop.
Well, you've only been going for 40 minutes.
Yeah,
So,
I have many slides on supernovae. Well,
maybe let's take a break and just say, does anyone have any questions so far?
Yeah.
And maybe that's quite a good break. And it's down to you, Jade. It's your talk. I mean, I'm happy to just take a quick break now. Does anyone have questions?
I would have one if no one else has.
Yeah.
So Jade, first of all, thank you very much for agreeing to participate and come and give your and give your talk. But I have 2 questions actually, and one is they are very general. Can you tell us what happened between the O3 and O4 in terms of improving the detectors? Is there any improvement of the accuracy or sensitivity in what way?
So I know that the distance out to which we can detect many of these sources improved a lot between, say, O2 and O3, and probably between O3 and O4. But as to like the technical improvements to the detector, like the instrumentation that allowed us to achieve that I don't know, because I just basically know nothing about instrumentation.
I see. Okay.
That'd be a question for Dan, I think.
Well, but I don't think he's present.
Yeah.
Jörg, maybe I can say just
sure.
I'm not an expert either, but the instruments are aging, and over the years, certain imperfections have appeared on the mirrors. And I know there's been work done to improve to counteract those issues with mirror imperfections. So that was part of the work. I'm sure there are lots of other things. I think there was some work done on further squeezing enhancements of the detectors. But yes, this is a question you should have directed to Dan.
Yeah, it occurred to me just now,
No worries.
Yeah.
One thing that I find is that the bigger the range on the detector is, the more messy the data is, like the more often it loses lock and the more glitches it's got in it. And then it usually gets cleaned up more as the run goes along. So yeah, whichever detector has the biggest range at the beginning of the run is usually the most messy, glitch-filled data.
Interesting.
I would have another question, but there is also a question in the chat. Maybe we do this first.
Hugh, yes. I don't know if you want to ask that question yourself, Hugh.
What were the sources of the two glitches?
Is there still that glitch thing where you can go and like help them find glitches in the data?
Yeah, so there is a tool called Gravity Spy where you can classify glitches yourself. They show you a glitch, and then they give you an option of like 10 boxes or something, and you can say which one you think it most looks like and put it in the box. And then they use all of those human classification of glitches to train machine learning algorithms to help you classify further glitches. So that's called gravityspy.org if you want to check it out. So this one here is scattered light from the lasers. And then this one here is caused by something called, I know it's caused by something called radio frequency beat notes, but again, because I'm not an instrumentation person, I don't really know what a radio frequency beat note is. I know that we had some others, like we had some ice on one of the detectors, and there was some glitches that occurred because this bird that was thirsty kept going and pecking on the ice to drink the water. And then some student that we sent to the detector to work for 3 months had to go walking down there with a hammer and had to literally go and hit the icy pipe with a hammer to see if they could reproduce the bird peck glitches, which they did. And then once that had been confirmed, they just put some insulation around it so the bird couldn't come and peck the detector anymore. So sometimes you have glitches where you can fix the problem, like with I think we called it Thirsty Raven. But then other times, like, getting rid of scattered light is something that loads of people work on, but it's just not easy to solve.
Yeah. A student being told, given a hammer, to go hit this in a multi-million dollars.
That's amazing.
Any other questions?
Yeah, I have a second one. And that's again a more organizational kind of thing. How is this actually organized in terms of the data streams that are coming? I would guess that the detector produces some sort of a raw data stream, and then that is somehow distributed. But are these modules that you are talking about, this what was it called, the Emily and OLIP and so on, are these run at the detector side, or are these distributed or run with the research groups already?
So we have a bunch of computing clusters where the data goes. There's one at each of the sites, and there's also one called CIT, which is, I think, is at Caltech. And I think that most of the data goes to CIT, and then the people who are running their searches in low latency, they will analyze their search on the CIT computer cluster. But there's, I don't know exactly how many, but I think 7 or 8 different LIGO and Virgo computing clusters, and the data gets sent to all of them pretty quickly. But yeah, it seems to be a preference for the Caltech one. So I think they might be the fastest.
I see. Okay. Thank you.
Okay. any other student have a burning question, even if you think it's an obvious one, because this stuff is not obvious, and it's really nice to just hear this talked about in so much detail. Or has Jade answered all the questions and is explaining it very well, which is also true. Okay. Well, I think that was it's just good to have a good break in it rather than a break. Maybe it's okay if people are feeling okay to like carry on. We can get on to supernovae just because I like supernovae. So I'm going to say let's carry on. But yeah, I mean, if you do, if a number of questions come up in the chat as we go through, I might interrupt Jade. Otherwise, I'll just if you think you're going to not need the 2 hours, you may as well just carry on that break. Does that sound okay?
Yeah.
Cool. Okay. Thanks. Carry on.
I need to shrink you again. Okay, so core collapse supernovae is my favorite source of gravitational wave burst because it's the one that I work on the most. So if you have stars larger than 8 solar masses, then you expect them to end their lives as a supernova. And the stars, massive stars, they develop ion group nuclei in their core. And then when they hit their effective transit mass, the core collapses and then bounces, and that causes a big shock wave that moves outwards. But then the shock wave stalls after a few hundred kilometers. And then you have this little diagram here where this is supposed to be the core, and then this is the shock wave that's been launched out from the core. And then this thing here is forming PNS's proto-neutron star. And then this starts to cool down after its big bounce. And it emits loads of neutrinos. And all of this energy from the neutrinos kind of gets stuck behind the shockwave and then powers the shock to make a full supernova explosion. So one of the great things about supernovae is that they would be a perfect multi-messenger source. So they emit electromagnetically from the outer regions. This is a simulation of the inner region of a supernovae from one of my simulations. But then they also emit neutrinos from in the core region, and also gravitational waves from in the core region. So if we get a supernova detection of gravitational waves, it could be the first time ever that we have a source that we've detected in both electromagnetic gravitational waves and neutrinos. So that would be exciting. So with optical supernovae, there's a huge number of detections. They get detected all the time. But the light that you see in a supernova, it comes hours after the collapse, because the shockwave has to reach the surface of the star before you start to see anything in electromagnetic light. And yeah, so it's emitted from the star surface, and because of that, it doesn't provide any information about what's going on right in the inner regions where the proto-neutron star is forming. So in neutrinos, we've only detected neutrinos from a supernova one time, and that was about 10 neutrinos from, I've missed the supernova part, supernova 1987A, and those neutrinos came right from the inner regions. But in gravitational waves, there's been no detection so far, although some people in the past have claimed that they found gravitational waves from a supernova, but nobody actually believed them. And they come directly from the inner regions, and you will learn so much things because of that. So they tell us about the explosion mechanism, the rotation of the core, the equation of state, the mass and radius of the proto-neutron star, loads of really interesting things. So what are the challenges? So one of the biggest challenges is the gravitational wave amplitude is low. So, but one good thing is that nobody who works on supernova simulations is confident about what the gravitational wave amplitude is actually supposed to be. And it actually differs a lot between different supernova simulation codes. So I'm hoping that we're wrong about the amplitude and we find one sooner than we think. the signals have some stochastic features. So yeah, in the time series, there is lots of stochastic parts of the waveform. And that's kind of because if you take, for example, this supernova here, this is the time frequency spectrogram again. So in basically all supernova simulations, you see this rising in frequency in time mode here, which is probably a G mode. Sometimes it's half a G mode, half some kind of other mode like an F mode or a P mode, they cross over and stuff. But for simplicity, we just usually call it a G mode. But you can see that the amplitude varies along the G mode, and that's basically the stochastic part of the signal. So we always know that how this, what this frequency is going to be with time, because the frequency is dependent on the mass and the radius of the proto-neutron star. So it gets more massive and smaller radius over time, and then the frequency goes up. But where these little spikes in amplitude are going to be, that's the stochastic part. And that's basically because there's like loads of matter falling down onto the forming neutron star. But you don't know how often and how hard it's going to hit. So someone described it as like you're hitting a bell with a hammer and then it rings, but you can't predict how often and how hard the hammer's going to hit. And so yeah, in the time series waveforms, as an example here, you get spikes that you don't know when they're going to occur, and then you get these little amplitude blobs in the waveform. But some of the other problems we have is, if we take, for example, this gravitational wave signal here, this is from a rapidly rotating supernova, and if you're rapidly rotating, you get this big spike at the core bounce time. But this simulation ended after like 20 milliseconds, and a supernova signal is several seconds long. So this is a big problem that we have in gravitational wave data analysis land, is that you can't really see how well you can detect a signal if you only have a few milliseconds of that signal and you don't know what the rest of the signal is going to look like or how loud it's going to be. So that was a major problem. And then we have signals like this one, where they've also simulated for, this is like 350 milliseconds, so much longer than this one. But still, you can see the amplitude of the gravitational wave signal is like rapidly growing at the time that they ended their simulation. So you never even know like what the rest of the signal looks like, what amplitude is it going to reach. And then people are saying, oh, you can't detect supernovae because the amplitude is so low. And then I'm saying, you don't even know what the amplitude is going to be because you cut your signal off before you even reach the maximum amplitude. And then we have some problems with people use too small of a sample rate when they did their supernova simulation. So in this simulation here, this G mode here is supposed to continuously increase in frequency of time, and it should go up here and keep going. But because they used a really low sample rate in their simulation, they've got some like boundary here, and you get some Eliason effect where the gravitational wave signal is being reflected back down at the boundary and then starts going down this way instead of increasing with frequency and time. So basically all of this high frequency content of the signal is just wrong because their sample rate was too low. Yeah, and you can do good searches or parameter estimation if you don't have good signals. So this is one of the reasons why I, as a LIGO person, started doing supernova simulations, is because I needed some good waveforms. And lots of people who work on supernova simulations, they like the gravitational wave signal isn't their main priority, and they're looking at other bits of the physics that they're concentrating on. So yeah, they just give us the gravitational wave signals as kind of like a side product of their project that wasn't their priority. So yeah, so I wanted to make some gravitational wave signals that would be good for gravitational wave data analysis. So when you model supernovae, you have to worry about the hydrodynamics, the equation of state, the neutrino physics, the gravity, the progenitor conditions. And there's a lot of stuff, and there's a lot of physics. And it's super hard to simulate it all, mostly because we just don't have enough computing power to do all of these things at the same time. So when you have your supernova simulation, it outputs these things: neutrinos, the gravitational wave, explosion energy, remnant properties, light curve, spectra, nucleosynthesis, explosions, pulsar kicks and stuff. But because you can't do all of these things at the same time currently, you usually have to cut corners in different areas depending on which thing you're looking at. So because I care about the gravitational waves, I might cut corners in areas that would mess up my light curve or my nucleosynthesis or something, but give me a good gravitational wave signal, whereas other people will do it differently. But maybe in the future, supernova, either our computers will improve or our supernova modeling will get faster, and then maybe we'll be able to do all of these things at the same time. So this is an example of what a typical supernova gravitational wave signal looks like. So this is the frequency and this is the time, and they all have this rising in time, rising in frequency with time, G mode signal. And this G mode frequency is related to the mass of the proton-neutron star and the radius of the proton-neutron star by this, m/r squared. And so by measuring this G mode, you will learn something about the properties of the proton-neutron star. And then the SASI, which stands for standing accretion shock instability, is basically instabilities in the shock wave that affects your gravitational wave signal. So because they're more related to the shock wave moving outwards, then if you measure this lower frequency SASI mode here, then you learn about the mass of the shock, the mass inside the shock radius, and also the radius of the shock wave, which is also be pretty cool to know about that, because all of these things, the shock at this time is like well inside the center of the star, where you're not going to learn anything about it from EM, and also the proton-neutron star as well. You can't learn about that from electromagnetic observations. So all of these would be pretty cool to learn about from the supernova signal. And with this SASI mode, it increases in frequency with time like this until the star explodes. And then if the star explodes, it either completely disappears or it just starts to decrease in frequency with time instead, which is what happened in this one. And also in my simulations, the amplitude of the gravitational wave emission always peaks after the shock is revived. So here's where the star exploded. The SASI starts to die away and the G mode gets a really high amplitude. So you can tell from the gravitational wave signal when the star exploded or if it didn't explode at all. And you can learn something about the proton-neutron star, and you can learn about the shock wave. So that's a lot of cool stuff. So we kind of split the waveforms into different types. And so the most common kind of supernova is the neutrino-driven explosions. And these are the ones where the shock stalls after a few hundred milliseconds, but then is repowered and you get a full supernova explosion by absorbing some of this energy from the neutrinos. And when people do supernova simulations of neutrino-driven explosions, they almost all do not include any rotational magnetic fields whatsoever. And so here's an example here. This is the shock radius of the star. This is the time after the core bounce. And so in these two supernova here, the shock is revived here, and then you get a full supernova explosion. So these are the neutrino-driven explosions. And then here's one here where the shock didn't revive, and it's just the shock radius is just staying low. So in the neutrino-driven explosions, you always get this G mode signal. The rise in frequency of time is really clear in this 18 solar mass model. And you get a little bit of low frequency SASI emission, but it just goes away once the shock is revived. And the amplitude peaks here after the shock revival. And the amplitude of the signal varies a lot depending on the progenitor mass, and also somewhat on the structure of the progenitor star. So if you have a nice 18 solar mass model, then it has lots of amplitude. You probably detect it, if we're right about the amplitudes, throughout the whole of the Milky Way and LIGO as it is now. But if you have a tiny little 9 solar mass thing, then you probably only get it like out to the galactic center or something. They have hardly any amplitude if the mass is tiny. But they always look like this in a time frequency spectrogram. But in the time series, they all look different because of the stochasticity. So what about the failed explosions? So in that case, this is this red one here where the shock never gets revived. So in that case, there would be no electromagnetic signal, but because the gravitational waves and neutrinos start from the core bounce time, you would still get a gravitational wave and neutrino signal, but no EM supernova. So because most of our simulations ended when we ran out of computer time, rather than for some like astrophysics reason or something, then it's possible that some of these models that we call failed explosions, would actually probably explode later if you actually could simulate the supernova for longer. So yeah, which ones do and don't explode? It's kind of hard because we don't have enough computer power we can see which ones explode pretty quickly, but the ones that explode at a later time, you can't even tell if they're going to or not, because you just run out of computer power before you get there. But then there's some things that you can plot that show that like, oh, maybe this model is going to explode soon. And so I have some where, I simulated it for like 600 milliseconds or something and it didn't explode, but some other things indicate that maybe it would have exploded soon if I continued it for a bit longer. But yeah, we can only dream of more computer power. And so if you have these failed explosion models, because of the, like I showed in the other ones, the gravitational wave amplitude peaks after the shock is revived here, then they generally have a lower gravitational wave amplitude than models that have exploded. So here's an example of a failed supernova explosion gravitational wave signal from a paper by O'Connor and Couch. Is a 20 solar mass progenitor model from MESA. This PERT thing just means that they added perturbations into the MESA model, which is something that you do for almost all supernova simulations. But it seems that, but in this one, they did some with them, some without perturbations, which is why they labeled the ones with perturbations. But I've learned that because a lot of other simulations don't specifically state that they added in perturbations, that some people just don't even know that they're there. But perturbations is standard, they're always in there. So I don't have to keep telling people about the perturbations. So yeah, the failed explosions, they still have this high frequency G mode, rises in frequency with time, and they have stronger low frequency gravitational wave emission from the SASE. So because the explosion never occurs, this low frequency mode just keeps going. It doesn't die off, and it increases in frequency with time a little bit. And so you have a really long gravitational wave signal, but it's also low amplitude. So then there's also black hole forming models. And sometimes they even undergo neutrino-driven explosion first, but then quickly form a black hole before the explosions even reach the surface of the star. So here's some examples here of some models I did. These are really massive models, 85 solar masses and 100 solar masses with no metallicity and different. These are the different equations of state that I used. So this is the shock radius, and this is the time after the core bounce. And then for these three models here, they undergo shock revival here, or there and there, and then the shock keeps expanding, and then here they just formed a black hole. So yeah, these were actually stopped because they formed a black hole rather than I just ran out of computer time. And then these ones here, these were stopped because I did run out of computer time, and they hadn't exploded or formed a black hole yet. But this one here showed strong indication that it was just about to explode. So I think this also would have exploded very shortly if I could have continued it for longer. And then, yeah, eventually would have formed a black hole because it's so massive. So you can see here is the 3 different equations of state for the 3 different colors, and the different models with different equation of state, they exploded at different times, which you can see on the gravitational wave signal, and also they form a black hole at different times. And so from these black hole forming models, the gravitational wave signal might be able to inform us about the equation of state. The neutrino emissions should just suddenly disappear. And I think you can learn about the progenitor mass from that, which would also help you like untangle the mass and radius that you would measure from the gravitational wave signal. For the gravitational wave signal, it's kind of harder to measure the cutoff because I'm not quite sure how you would be sure that the amplitude wasn't just too low for you to detect, or if it is cut off because it's formed a black hole. But yeah, I guess we can still look into that. But if the neutrinos suddenly disappear as well, then we would be sure that the gravitational wave signal also stopped because they've formed a black hole. And this is what the gravitational wave signals look like in the time series for the black hole forming models. They have really large masses, and so that made really high gravitational wave amplitudes. But for the 100 solar mass models, they just pretty much, yeah, they have really high amplitude by there for some reason. I'm not sure what happened then that made it go so large. And then these ones here, the 85 solar mass models, they kind of look pretty similar in the time series. They have this this deviation from 0 occurs at like really low frequencies below 10 hertz, and it has this really big amplitude. But to measure the low frequency part of a gravitational wave signal, you need a really, really long duration signal. And most supernova simulations have to stop because they've run out of time. So nobody knows exactly how big this low frequency part of the signal gets. Although maybe you could tell better if you do like 2D simulations or something that would run faster. But you can detect these low frequency parts of the signal anyway in the LIGO, Virgo, or Cagra frequency band. So once you filter these waveforms so that you only keep the frequencies that's in the, say, between 30 and 4,000 hertz in the LIGO frequency band, then the signal will go back to being centered on 0 again, because this deviation from 0 is all it's all low frequency content. But if in the future we build like a gravitational wave detector on the moon or something, which would be good for that kind of frequency band, then maybe investigating this more would be a good idea. Maybe we'll be super sensitive to supernovae with a moon detector or something. And then this is what the black hole forming models look like if you take the spectrogram again. So they have this rise in frequency of time, G mode, just like all the other models, and a big, strong, low frequency SASI mode because of the no explosion for this 100 solar mass models. And then for the 85 solar mass models, the SASI mode increases and then dies off, and you get the G mode. And then the yeah, a big spike in amplitude there just after the shock is revived. But you can see that it's kind of hard to see where exactly does the signal stop once you form a black hole in the gravitational wave signal, because yeah, this is just kind of turned into a broadband blob by the time you're getting close to the black hole formation time. So it's not really clear if it's just like, did the amplitude get too small, or did it form a black hole? So those was all from my simulations, but other groups show similar things. So this group in Taiwan, and they have some black hole forming models. And so they have, this is their shock radius here in the time. And they have this green one where the shock isn't revived. And then this red one where the shock is revived really quickly. And then this blue one where the shock is revived at a later time before it forms a black hole. And then you can see in the gravitational wave signals here, in this pink one, they have this, you just see the G mode. You don't see any low frequency mode. And I think that's just because the shock revived so quickly that it didn't have time to form this low frequency SASI mode. And then in the green one, it has a nice strong low frequency mode. It has quite a lot of modes, visible modes in there. Yeah, and then in the blue one, the low frequency mode here loses a lot of amplitude at later times. So all of those are simulations that include, don't include rotation, don't include magnetic fields. But if you do include rotation, then you significantly increase the amplitude of the gravitational waves. So here's an example, and you get this massive spike at core bounce in the time series. And it only occurs in the plus polarization. In the cross polarization, you get nothing. And I think it only comes from the equator. So if the pole of the star is facing the Earth, you're not going to see the core bounce either. But the amplitude of this spike is directly related to the rotation. So you can literally do like time domain parameter estimation with these core bounce signals to figure out what the rotation of the star is at the time when the core bounce is, which is really good. And so loads of people have looked into that. So there's loads of these papers where they have hundreds of these core bounce signals for rotating supernovae, but nobody bothered simulating them beyond like 20 or 30 milliseconds. So nobody knew what the rest of the gravitational wave signal would look like. And there was lots of studies about how you can determine the explosion mechanism of the star, because as well as getting the, the explosion being caused by energy from the neutrinos, you can also have explosions that are caused from energy from rotation and magnetic fields. And so some people simulated these core bounce supernova simulations with magnetic fields and rotation, and then just called them magnetorotational explosions, but nobody actually really knew if they were going to be magnetorotational explosions because the simulations was ended before the shock was even revived. So it was just kind of guessing that like, oh, if you have rotation and magnetic fields, then you're going to get a magnetorotational explosion, but not knowing for sure because they didn't simulate the supernovae into the explosion phase. And so if you want to do some kind of model selection study of your gravitational wave signal to see, or was the shock revived by the neutrinos, or was it revived by the magnetic field, then you can't really do that accurately with a 30 millisecond gravitational wave signal. So first we did some neutrino-driven explosions with rotation. So we added in rapid rotation, but didn't put any magnetic fields in. So the explosion is still going to be neutrino-driven, because to get a magnetorotational explosion, you have to have rapid rotation and magnetic fields. So we simulated this 39 solar mass star. This is the time series of the gravitational wave signal. We went out to 1 second, and this is the spectrogram. Don't show the core bounce in this part of the signal, but yeah, it is there if you're at the right angles. But you can see it here in the spectrogram, and then it just has this same looking G mode that we get in the neutrino-driven explosions that don't have any rotation. And rotation significantly increases the gravitational wave amplitude. So this is amplitude in centimeters, because that's what the supernova codes that give out amplitude in centimeters. But for a regular neutrino-driven explosion, you get like a 10 centimeter amplitude. And if once you add in rotation, it goes up to like, this one went up to 40. So that's a lot of extra distance for detecting these if there's some rotation. And so we knew before from the regular neutrino-driven explosions that this frequency here, the gravitational wave emission, was related to the mass of the proto-neutron star divided by the radius squared. But if you add in rotation, that is no longer true. So there's a whole bunch of work into understanding the relationship between the proto-neutron star and the gravitational wave frequency. And once you start adding in rotation, none of them hold true anymore, and they don't fit your gravitational wave signal anymore. So even though the signal kind of looks the same as when we didn't use rotation, now our understanding of how you relate this signal to the proto-neutron star properties doesn't hold anymore. So understanding how you learn about the star once you have rotation in your gravitational wave signal is something that's still an ongoing area of research, and nobody knows how to answer that yet. So then we looked at magnetorotational supernovae. This is a picture from one of my simulations. And so magnetorotational supernovae, they have a huge amount of energy, and the magnetic fields extract the rotational energy and then power these really powerful magnetorotational explosions. And so all kinds of like extreme things like hypernovae and long GRBs are thought to maybe be these magnetorotational explosions. And they have smaller rates than neutrino-driven explosions, but also they have a lot more gravitational wave amplitude. So recently, people have started to do some of these magnetorotational simulations in 3D, and there's a group of people in Europe who've mostly been doing this, but most of their papers just don't include the gravitational wave emission because they've just been interested in other aspects of the supernova and just didn't include it in. Or we have some of these older ones that included rotation and magnetic fields, but then only did the first 30 milliseconds. Or we're only in 2D, and there's some older ones that are 3D, but they use equations of state that were great at the time, but now everyone thinks they're rubbish. So they're not that great either. So the next thing we decided to do was, let's do some magnetorotational simulations. So then I got my 39 solar mass model again, and kept the rotation rate same, but then added in 2 different magnetic field strengths of 10 to the 10 Gauss and 10 to the 12 Gauss. And so here's an example of what the gravitational wave signal looks like. So this is the time series. Can't learn much from that, but in the spectrogram, you can see you get this rise in frequency with time. It kind of looks the same, but I don't know if you noticed, but the frequency is now much higher. So this one goes up to like maybe 2000 hertz, whereas if you go back to my other one, where is it? Yeah, this one only goes up to 1000 hertz. So by adding in magnetic fields, I got a much larger, a much higher in frequency gravitational wave signal. And the frequency is super important because the gravitational wave detectors are very frequency dependent. So if your frequency of your signal changes, then you're changing your detectability as well. And the gravitational wave signal amplitude is much higher. So if you remember, the last one went up to 40 centimeters, and now I'm up to 100 centimeters. So more than double. And so it seems to be the fashion now that everyone is doing simulations from hadron quark phase transitions. It's not something that I know a lot about, but there's this paper by Pia, who's at Monash, that's just come out very recently. And so this is her simulation here. And this is a 35 solar mass supernova. And you have this G mode signal here, just looks normal, regular equation of state. And then here she simulates the same model with a phase transition equation of state. And then as well as getting this G mode here, she also has this G mode here decreasing in frequency with time one. So yeah, so when we come to doing like explosion mechanism studies, it's possible that as well as neutrino and magnetorotational explosions, we might also be able to do some phase transition explosion studies too, if these signals, features in the signal hold up. And then there's also this study by a Japanese group, and this looks very different as well. And so they have this 50 solar mass model and a 70 solar mass model, and they have all these big, like, long broadband features. And they don't really look much like PS simulation. So yeah, I guess this is still a ongoing area of research in supernova land. This seems to be quite fashionable at the moment. So when we search for supernovae in our LIGO, Virgo, Cagra supernova searches, we also look for some really, really extreme stuff. And one of those is just like a rotating ellipsoid. So this kind of looks like this. And so we use like basically a sine Gaussian waveform, but it has some also physical parameters in there. Like we've got this momentum of inertia and the ellipticity. And so this kind of extreme rotating ellipsoid kind of supernova would have like really, really high gravitational wave emission. And then you could, by not detecting it, you can put constraints on the ellipticity of the source of the gravitational wave emission, or source of the supernova that has no gravitational wave emission. So this is one thing that we look for in our supernova search papers. So here's some plots of detectability of some of my models. So if you have one LIGO detector, this is my 18 solar mass model here, which I'm going to call typical supernova. It just goes out to say, I don't know, 30, 35 kiloparsecs in LIGO, one LIGO detector. If you have multiple detectors, you get a bit more distance. But this is basically galactic at the moment for a regular supernova. And then if you have, this is my model with rotation here, and that goes out to almost 150 kiloparsec. And then if you add magnetic fields again, here's my two models with magnetic fields, you get even more distance, so beyond 250 kiloparsec. And this is just the energy of the explosion, because yeah, as the explosion gets more energetic, you get more distance. But also this energy of the explosions in the simulations is way smaller than the energy that you see in supernovae, because these ones are supposed to be like 10 to the 51 erg, and these ones 10 to the 52, which they're very clearly not. So I'm kind of hoping that when we fix this problem with our explosion energy being underestimated, that we'll also get a bit more gravitational wave energy. But I don't know if that'll really happen or if it's wishful thinking. But yeah, it's definitely some issue there in everyone's supernova simulations. And then here in Cosmic Explorer, you don't even hit 1 megaparsec for the 18 solar mass model. And then you get a couple of megaparsecs for rotation and models of rotation and magnetic fields. And this is just with one Cosmic Explorer detector. And if you get multiple detectors, you get more distance. And I think you need a good couple of megaparsec before you start seeing one supernova a year. So I think if we were going to detect one supernova a year, we probably need at least 2 Cosmic Explorer detectors. But even if it's a while before we can detect one supernova a year, there's still some hope, because we might get lucky and get one much closer than a few megaparsecs. And also we might just be completely wrong about the amplitude. I mean, we get the energy of the explosion completely wrong. So I wouldn't be surprised if we're also getting the energy of the gravitational waves completely wrong as well. So you can simulate a waveform for every possible supernova with every possible set of parameters. So if you want to do, like a whole template of different supernova gravitational wave signals, so you want to do some parameter estimation, then you really need some kind of phenomenological model, because you just can't do a simulation for every kind of possible supernova. So the models that we do make, they need to fit well the simulations that we do have, and they also need to predict what would the supernova look like in the rest of the parameter space where we haven't simulated yet. And we need to be able to make these waveforms fast for them to be useful for things like parameter estimation. And as I mentioned, the time series is just too stochastic. So for most models for supernova gravitational wave emission, you usually go for time frequency instead, where you see these common features. So here's an example here. This is for non-rotating. If it was rotating, you'd have a spike here. This is part of the signal called prompt convection that you often see. And then you get this G mode, which is the main feature, and sometimes a low frequency mode produced by the SASE. So we basically want a model that can produce all of these things for any kind of supernova. So in this paper here, they use a phenomenological model to create a training set of supernova waveforms for a supernova machine learning search. So here's an example here of one of their fake supernova signals. And they only model the G-mode part. They don't try to use any other parts of the signal yet. And their model is a second degree polynomial that has all these parameters. So it has like an initial time, an end time, a starting frequency, an ending frequency. Can't remember what Q is. And then F driver is the way they made their stochastic part. So the driver thing is like the amplitude along the G mode. And in this paper, they make a whole template bank of these phenomenological models. And I think they pretty much look like supernova to me. And then they test it by adding one of their models into the gravitational wave data and then finding it with their machine learning search. So yeah, I think their next steps would be to like test it on, see if they could find like a NR supernova waveform using their models instead of finding another one of their models with their model. Yeah, and adding in the other supernova features. So they're making some progress with this kind of thing. So then I also have a paper where I try to model a supernova signal using an asymmetric chirplet model. So an asymmetric chirplet in a time series looks like this. So it's kind of like a sine Gaussian, but the frequency changes with time so that you get this rise in frequency with time. And yeah, it kind of just looks like the G mode in the time frequency. And then once I reconstruct the gravitational wave signal using this asymmetric chirplet model, then I try and relate it back to the supernova source parameters using these universal relations that come from this paper by a guy called Alex, who's at Valencia. And so he has this equation here. This is the gravitational wave frequency, and he says that of the G mode, and he says it's determined by this equation, where x is the mass and radius of the proton-neutron star. So this is my actual simulation of an 18 solar mass supernova signal. And then this is what my reconstruction of the supernova looks like using my asymmetric chirplet model. So one thing you can see is that I don't have all the little stochastic bumps in, but I just have one solid mode. But I don't think you need the little stochastic bumps to be able to measure the mass and radius of the proton-neutron star. You just need to know like what the frequency is at each time bin, which you could do with the model that I made. And so using those universal relations, we then converted our reconstructed signal into m over r squared. And so this thin dark blue line is the real m over r squared of the proton-neutron star from my simulation. And then the light blue is the actual M over R squared that I measured using my signal model and some Bayesian parameter estimation code. So it's pretty good in the early times, and then at the late times it gets not so good, and at the really early times, because of the signal amplitude gets lower and the G mode gets a lot broader. So yeah, we're trying to make making some progress in trying to show how we can actually learn something about the supernova source parameters from the actual gravitational wave signal. Yeah, so another thing that we try to do is measure the actual explosion mechanism. And to do this, we usually use Bayesian model selection and principal component analysis. And some other studies have used neural networks and some other technique called dictionary learning. I'm not an expert in dictionary learning. But previous studies had no good waveforms for the magnetorotational explosion mechanism. So like I said earlier, we just, for supernovae that had rapid rotation and strong magnetic fields, we just had these 30 millisecond waveforms. We don't even know if they really do explode by magnetorotational mechanism, because they're not even simulated out until the explosion time. So we have all these methods trying to determine the explosion mechanism of the star with no good waveforms to even be able to tell what the gravitational wave signal should look like if it is a magnetorotational explosion. So that was one of the reasons why I did those 239 solar masses models with magnetic fields. I've also done a couple of 15 solar mass models with rotation and magnetic fields. And there's also a group in Valencia, and they've also been doing some magnetorotational explosions. And so we've now joined forces so that using my waveforms and their waveforms combined, we can now try and actually see if we can determine what the explosion mechanism is using our new waveforms. So so we're currently writing this new paper where we consider 4 models, which is the star does not explode, there's a neutrino-driven explosion, there's a magnetorotational explosion, or we just have some chirplet model, which isn't even a supernova, it's just a random thing that looks a bit like a supernova. And then we try to distinguish all these models using all these different classification techniques, and then we compare the techniques as well and see which one's the best. So the things that wasn't a supernova, basically, this is the true explosion mechanism, and this is what we get from our classification, and then you want the numbers to be big down the middle if you've got the right answer. So for these things that's not even a supernova, we get 100% classified as not being one of a supernova. Then for the magnetorotational explosions, we get 76% correct, and the neutrino mechanism 75, and the non-explosions is not so good, only 58. But the reason for that is that this to tell if the model didn't explode, you usually need this this low frequency SASI emission to be visible in the signal, and the SASI part of the signal is usually much lower amplitude than this G mode part of the signal. So if the signal to noise ratio is low, you're only going to see the G modes, you're not going to see the SASI part, and so then it's like basically impossible to tell if it's from a non-exploding model or not. Well, at least just from the gravitational wave emission, you might be able to tell from the lack of electromagnetic signal. But we wasn't really sure how this was going to go, because the G modes between the neutrino-driven explosions and the magnetorotational explosions and the non-explosions, they all look really similar. So it's like a very difficult classification problem. But so we were kind of happy that at least for the neutrino and magnetorotational explosions, that we can actually tell them apart just from looking at this gravitational wave G mode. So what about searches? So you can't do a template-based match filter search for supernovae like you do for compact binaries. And in previous observing runs, there's been no supernova specific search codes. So what I mean by that is that when we search for supernovae, we've used the generic CWB burst search that can just search for any burst signal. And we haven't taken into account the fact that we actually know some things about what the supernova signal should look like. So there's this new search called Molassic that actually does take into account some of the expected features of a supernova signal that's going to be used during 04, but I'm not really going to get into that. And there's a lot of development work going on that people are trying to make gravitational wave supernova searches where you actually account for the signal shape in some way, because in 01 and 02 and 03, we didn't do that. So I'll show you some of the results from what we did do. So in the 01 and 02 supernova search, we targeted 5 supernovae, and this here is the Milky Way, and this is their sky position. This one was 19, these 3 are all 19 megaparsec. This one's 15.2, and then this one's 6.7 megaparsec. So as you may have noticed, these distances are way larger than the distances that I said we think we can detect supernovae out to, but also we're really not sure about the amplitude of the gravitational wave emission. So we're kind of targeting all supernovae that go out to 20 megaparsec, just in case we're wrong about the amplitude. And there's a few details there about what we knew about the stars. So then we have an on-source window. There's this really nice paper by Jasmine Gill that explains the method of how do you detect the time window for where you expect the supernova gravitational wave emission to be, depending on what you measure in EM. So, but I'm not going to get into that either. I'll just show you the actual windows. But you basically just, you measure, you observe the supernovae in electromagnetic signals, and then from what the best you can learn from that, which varies a lot depending on how quickly they saw the supernova, you can kind of extrapolate backwards to figure out when the core bounce might have happened and the gravitational wave emission might have occurred. So usually if the window is really big, it's because you didn't have, you usually saw the supernova a bit later. And then these color bars is when we had gravitational wave data within the window. So you can see, like for this supernova, there was like huge amounts of time where the supernova might have occurred and we didn't even have any gravitational wave data there. So yeah, we just have to use what we've got and hope that we didn't miss it. So here's the results. These are the false alarm rates and the false alarm probabilities for people who care about those things. But this is basically, this black line is the background. And if you had some detection, there should be some event over here somewhere, and there's not. So we did not detect any supernovae in, I wrote 0101, but it should be 0102. Yeah, no supernovae in 01 or 02. Then in 03, I think we kind of got unlucky because we have 9 supernovae, but their distance is between 16 and 28 megaparsec. Whereas if you remember for the 0102 search, we had one at 6 megaparsec. So they're all pretty far away. But one thing that I think was really cool is that 2 of them exploded in the same galaxy in the same week. So this first supernova went off, then everyone pointed their telescopes over there to look at it, and then the second one went off. And then because everyone was already pointing their telescopes at that galaxy, they got really good information about that second supernova because they saw it straight away. So I thought that was really cool. And I really hope that our own galaxy would give us 2 in 1 week. That would be like my dream. So these are the on-source windows. They're pretty big. Everything is preliminary because the paper's not published yet. But they're basically, the longest ones are about 8 days. It's quite good data coverage in the boxes though. We have the percentage there of how much of the on-source window actually has gravitational wave data. So then this is the search results. And so we had two events that were interesting. The first one is already published as being a binary black hole, but it doesn't even look that much like a binary black hole. It doesn't fit the template very well because it's really short duration. But we removed that from the results because everyone thinks it's binary black hole. And then for this supernova here, we also had an event that was 2.78 sigma, which is not big enough for us to say it's a detection, but we did get momentarily excited. So this is what it looks like. It's just kind of like a line, 800 and something hertz, but we think it's highly likely to be some kind of detector noise and not actually a supernova gravitational wave signal, even if it was 2.8 sigma. So I guess that was more interesting than 01 and 02, but probably almost definitely not an actual gravitational wave signal. So yeah, maybe we'll get more lucky in 04 and have some nearer supernovae. Yeah, and because all the supernovae were far away in 03 and the results are just not that interesting, because we can't even produce better upper limits if the supernova are further away than they were in 01. So we're not even sure at this point in whether this is going to be a full LIGO Virgo Cagra collaboration paper, or I think we're probably just going to publish it as a short author paper with the people who are involved in the analysis. But yeah, I'm not important enough to make that decision. Someone else will decide. Yeah, so now I've come to the end of my talk. And so, yeah, I guess the main thing I want everyone to know is that like 5 years ago, we had rubbish waveforms, but for supernovae. But now we're doing lots of supernova simulations with gravitational wave analysis in mind, getting much better waveforms. And but there's still a long way to go. Like, we're not sure what the gravitational wave amplitude should be. Our searches are not the best for supernovae. We still don't understand the relationship between the source parameters and the gravitational wave emission if you have like rotation or magnetic fields. And so there's still loads of cool work for us to do. But yeah, I'm keeping my fingers crossed for a nearby supernova soon.
Great, thanks very much, Jade. That's cool. Cool. Questions? Anyone? It's really cool though, seeing all these waveforms. And so we can't get close to supernovae. It's a problem.
Hi, Jade, can I jump in?
Yeah.
I should turn my video on. I'm actually on study leave, so I'm a little bit unkempt. That was a fantastic talk. I really, really enjoyed that, and heaps to probably to ask you more about at some point. Maybe I was going to ask about the gravitational wave amplitudes you mentioned there. I know things aren't linear, far from it, but suppose I scale up the energy. I know I'm off by a factor of 10 or maybe 100 in my supernova energy. If I scale up my gravitational waves with that kind of energy, can I back out an amplitude that might be plausible, quote unquote, and then we could sort of redo the searches for that?
I was trying to understand. Do you mean like if because we know that the overall energy is underestimated?
Yeah,
we could just increase the gravitational wave amplitude by the amount we know the overall energy is underestimated, and then see if that would improve the distance.
I'm not saying that's physical, right? That's why you have to run the simulations, but just as sort of a quick and dirty calculation, would that give us some idea?
Yeah, so if you like, quick and dirty did that for LIGO or for our current detectors, it wouldn't really make a lot of difference, because once you get past the galaxy and some of the nearby things like the Magellanic Clouds or whatever, there's just too much empty space. So if we go from, say, I don't know, 30 kiloparsecs to 300 kiloparsecs, you're not actually going to increase the rate much because you're just mostly gaining empty space. But then when you go to the next generation of detectors, if you increase it from like, I don't know, 800 kiloparsecs to 8 megaparsecs, that's like a massive increase in your rate of supernova detections then. So I think like maybe for the current detectors we have now, like increasing the amplitude isn't going to make a huge difference because of all the empty space. But for the next generation of detectors, I think even little increases in amplitude is probably going to make a big difference to whether we actually see one or not.
I also have a question, if I may. I assume when you compute the gravitational wave amplitudes, you use the quadrupole. You compute the quadrupole. What kind of things do you include? Is this mostly the mass quadrupole, or are there other things included there?
Yeah, I think it's mostly the mass. I don't really think about it too much because it's kind of a thing that, like, you know, someone just writes it once and then you use it.
It's just a module somewhere. Yes, I can. Yeah. No, I was thinking that maybe one can include also the electromagnetic waves that are emitted, because that's also a source of gravitational waves by themselves. It could just be that it's way too small compared to the mass quadrupole, but it's a reasonable thing, I think, to think about.
Yeah, so for the simulations we do, it's like right at the very beginning, like the first 1 second before before there's any, you know, electromagnetic things escaping. But I guess they're still going on in the inside, even if they're stuck.
Yeah, okay. It could well be that they come at different timescales, and then that's a different things. Yes, right.
Yeah, there's quite a few things at different timescales, because the actual supernova signals are probably going to go on for like a really long time, like several seconds or longer, until, I don't know, you could form a black hole some long time later, or you just have your neutron star settle down or something. But yeah, we mostly just do the first 1 second and then run out of computer power. So I'm not too sure, like, what even the rest of it looks like, or what would the gravitational wave signal look like when it actually forms the black hole, because our simulation codes, they just break at that point. They don't know how to handle that. That's I think there's some people at Monash actually who are trying to code that up so that you can actually simulate that part where you get the black hole formation.
I had another question about the equation of states. I mean, which ones or what kind of equation of states are you using? Are these tabled ones that come from nuclear physics or whatever is relevant?
Yeah, so they are all tabled ones.
Yeah, okay.
I have some listed somewhere.
So it's not just the simple ones that rho is proportional to the energy density or to the pressure and stuff like this. It's really computed EOSs, right? Yeah.
So this Latimer one used to be really popular in supernova land, but now everyone seems to be moving to these SFHO, SFHX ones. But yeah, I just have a folder full of equation of state tables and then use whatever one I like.
Yeah, but one sees that there is a difference. I mean, different equations of states have different consequences. That's definitely true. I mean,
yeah.
So it is important. Yeah, it
is important.
I just think it's good to actually have some supernova simulations that explode, because that was always a problem.
Yeah.
I think it's amazing that also neutrinos drive that when the shockwave stalls. I think it still blows my mind when I think of how hard it is to detect them. They do that.
Because
with the numerics, actually, Jade, is it the issue that you're trying to simulate greater and greater volumes of space that makes it harder to run them for long times?
Yeah, so with mine, you need good spatial resolution right in the center because we care about what's going on in the protoneutron star. But usually if you're looking at something else like light curves or whatever, then maybe you don't care about that. So you would change your resolution so that you can simulate for longer, and then you can't measure the gravitational waves. So you can't really do the big scale long stuff and the small scale short stuff all at the same time at the moment. Or sometimes you start off with you do the first part with one code, and then you'll map it to some other code that does it on a different scale to get the other parts.
Are there any students have questions? Because it's always difficult to ask questions, and if you want somebody who's going to give you a nice answer and be nice to ask questions to, it's probably Jade. So if anyone wants to speak up as a student, ask a question. We should have at least one student question before we move on. Death to silence. You can ask it in the chat if you want to. Okay, everyone is scared away. This is terrible. Or perhaps more likely that Jade just explained. I mean, it was a really great talk, Jade. So thank you very much. It was nice to have that overview of supernovae and all the different things that we can see. And it's nice to have these burst searches that are going to come out and how that's going to be in there for 04. Because you never know what we're going to find. That's what's great about this, right? It's just we've got to get lucky. So
yeah, I'm really excited that I get to co-chair the burst group during 04. So I really hope that we find the first burst whilst I'm the co-chair, because I think that would be like fun chaos. But maybe I won't get that lucky.
Yeah. I mean, it's always interesting, like when there's a supernova progenitor found. So this is like, it used to be chaos, because you've got all these supernova groups trying to compete. And if they find an interesting one, I wouldn't describe the chaos as fun, but it's maybe rewarding chaos, because you'll be rewarded with the chaos that you have to deal with. Okay.
I think there would be a lot of pressure on us from external communities as well, because if there's a nearby supernova, you're all going to know about it, and you'll know if our detectors are on, and you're just going to be asking us, did we see it? Did we see it?
Yeah. I'll be there. I'll get that ticket and join that queue. And and I'm sure it'll be like, we'll see the HST Twitter bot going, looking at binary neutron star merger, looking at gravitational waves from supernova source. Okay, if no one's got any more questions from Jade, or if Jade is all finished, I thank Jade once again. That was a really, really cool talk. And York has said that there are some students who wanted to make an announcement, apparently. So, don't know.
Yeah.
They wanted to speak up.
Yeah, I guess I will just start. Thanks, Jade, by the way. That was a really good talk. And thank you to the organizers for doing this. It's really great to have this sort of opportunity to listen to talks that are actually in our field for once. So my name's Elliot. I'm a PhD student at Monash doing a mathematical relativity. And myself and some other students from New Zealand and Australia have organized a student conference for May this year. So I know everyone's intimidated asking questions to actual scientists. So this is a chance for you to give talks and meet your peers and collaborate with people at the same sort of stage of research as us. So as I said, it's scheduled for May, and it's supported by Matrix. So they're an inter-university research group in Australia, and they help sponsor these sorts of conferences and symposia. And we'll have more information coming soon, but we thought we'd just announce it now so you guys can get excited and maybe start thinking about whether you would like to give a talk to your fellow students. Yeah, thank you.
Great, thanks, Elliot. That's cool. Where will it be? That's a good question from Ollie.
So it's going to be an online conference.
Okay.
Because students are poor.
Yeah. I mean, although you could always have hubs, right? So if people in Auckland wanted to come together, we could just hire one of our rooms, and I'm sure you've got rooms in other universities. That'd be quite nice. And
yeah, exactly.
and the real secret about people when they're giving talks is that everyone likes questions. So don't ever not ask a question because you think the person doesn't want the questions. But yeah, it's really nice if it's all just students, because, you know, you might feel slightly safer, and it is scary, but then asking questions is scary, and it's good to get practice, and that's a good place to do it. Cool. Is there any other announcements from the organizers? No, definitely science.
Nope.
Okay, well, that's good. Okay, good. Then thanks, Jorg. Thanks, Elliot. Thanks, Jade, very much. I suggest we all give Jade a Zoom round of applause, and then we'll all go to lunch. And you've got the next session, I believe, at 2:30. Is that right?
Yes, exactly.
Sorry about that. I died for some reason, but yes. So